talking about the awards. Sir is the awardee of GRF in the scheme entitled the Thermoluminescence and Lattice Defects in Lithium Oxide sponsored by DAE. Sir was awarded associateship by Physical Research Laboratory, Ahmedabad, for the work on development of highly sensitive quartz and feldspar-based phosphorus for dating applications. Sir has worked as a presiding officer in various Lok Sabha and Vidhan Sabha municipal corporation elections in the period 2004-2012. Dr. Patil is one of the member of founder team of Institute of Forensic Science, Nagpur. Now, I would like to request Dr. Patil sir to continue his talk.
Patil sir, welcome. Welcome to the STTP.
Okay, thank you. I'm just sharing my PPT.
Sir, could you please adjust the camera? You're not visible.
Sir, please adjust your camera.
Yeah. Okay.
It is okay, sir. Yes, sir. Okay.
Yes, it is okay now.
Now, are you getting this? Okay. Not sharing. Sharing. Is it shared presentation?
Pardon, sir?
I'm sharing another application. Problem is there, it is not sharing. 1 minute, I'll just.
Participants please stay connected. Some technical issue. Rectify and start.
खोल ये देखो ये नहीं ये फायर
Participants, please kindly wait. There's a technical issue. For the time being, I would like to elaborate that in the next session, afternoon session will start at 1:50, and we're having two speakers in the afternoon session, Mr. Sunil Mahabal and Dr. Shyam Deotali sir, and then we are having a graduation function at 4 p.m. So please kindly stay connected. Dr. Patil sir is joining us shortly. Kindly stay connected.
Speaker चालू. अच्छा. Good morning. Am I audible?
Yes, sir.
Yes, sir.
Are you getting this presentation?
Yes, sir.
Okay. F5 कमाल. F5. हाँ. Are you getting this presentation now?
Yes, sir.
Okay.
Yes, sir.
Okay. So, very good morning now. It has become good afternoon rather. I'm Professor Patil from Institute of Forensic Science, Nagpur. And I will be presenting this on this microscopes and their operation on this program. At the outset, I am very thankful to the organizers for giving me opportunity to interact with various faculties and members from this region. This topic I have made as simple as possible because looking into the audience from various disciplines. Okay, now microscopes are the essential part in our in the scientific world, because we use microscope very oftenly to see the micro things. Okay, so I'll just start with my this presentation. Now you can see the things that are there in the in the world, or you may say in the universe. So yeah, you can see the things size varies from say 1 mm, rather 1 meter to the 0.1 nm. So this is the size of the things that are there in nature. Now, out of which we can see some of the things with unaided eye. That is, say from some 1 meter or 10 meters to say lowest up to say 1 meter. We can see the things with the unaided eye. Now, this eye has a resolution to only see these things, that is up to 1 mm. Then we have the things below, that is below 1 nm to 100 nm. We can or some few micrometers, we can have a light microscope. We can see it with light microscope. Okay, so these things we cannot see with our naked eye. Then the things below 100 nm, it is very difficult to resolve by the light microscope. So we have another type of microscope which we call as the electron microscope. So electron microscope gives us vision from say 100 micron to up to say 0.1 nanometer. So this is the entire range of sizes of the things that we have in nature, and we require different types of instrument to see it. Okay, so this is just a glimpse of what we have in nature and what we want to see using the various instruments. Okay, then I come to the history of microscopes, because I feel that it is very essential part as to how the things were developed from the basic things to a most modern microscope. So the story of microscope started with 1000 AD. That is the first microscope was a simple glass sphere. Now this glass sphere, which usually is called as a reading stone. So it was a simple glass sphere which used to magnify the things on the reading materials. So it is a small instrument take a sphere with spear which you put on the table, some reading materials which are of very small size can be magnified. Now this was the first start of our microscope. Then 1284 Italian Salvano di Armanet invented the first wearable eyeglasses. So eyeglasses were discovered in this year. Then 1590, that is two Dutch glassmakers, that is Janssen and Hans Janssen and Zacharias Janssen, actually put two lenses in a tube, and this was the real start of what is called as a compound microscope and the telescope. Then comes 1665, where Robert Hooke looked the quark slice through microscope and saw that there are some pores on or cells in it. So quark material, it is a very porous material, and you cannot see the porosity of that material with the naked eye. But if you use a microscope, then you will see that there are pores in it. Then the real microscopy begins. In the biology world, when Anton van Leeuwenhoek built a simple microscope to see the micro things such as blood, yeast, insects, etc. So this was the real discovery of the micro things in a biological world. Then 1903, the most modern microscope was developed, which could study the object below the wavelength of light. And the Nobel Prize was given to Mr. Richard Zsigmondy in 1925. Then the most improved microscope was invented by Fritz Zernike, who invented what is called as a phase contrast microscope that allowed the study of colorless and transparent biological material. And he also won the Nobel Prize in Physics in 1953. Then comes the Ernest Ruska for his electron microscope, and then the last one in the microscope family was the scanning tunneling microscope. Now this is the brief historical background of the microscope, from the modest microscope to the most modern microscope, that is the scanning tunneling microscope. Now this Antony van Leeuwenhoek he was the first person to observe the microorganism very accurately. See, these are the pictures he had drawn, because in those days there was no camera, so you had to draw the things what is observed. So these are the various microorganisms he observed under the microscope. Now we come to the basic principle of the microscopes. Now for that, we'll revisit the various things which are necessary to know how the microscope works. The first is the light. It is an electromagnetic wave, and the wavelength is 400 to 600 nanometer in the visible region. And any object is visible when light strikes it and get reflected into the eye. So what we see is because of the reflected light from that object. Then there is a phenomena of reflection, transmission, and absorption of light. Whenever the light is put on any surface, it is either reflected, it is absorbed, or it is transmitted. So I have just given in this picture that how the light, what happens to the light when it strikes any object. Then there are three parameters of light that contains the information about the object. The first is the amplitude, that is the intensity of light. So dark surface absorb light, so reflected intensity is less, and hence the object appears dark. So whenever any object is subjected to light, if it is a dark object, that means it will absorb all the light, and no light is reflected, therefore it will appear dark. Bright
Sir,
surface. Huh?
so sorry to interrupt you, but you haven't made the slideshow.
Huh?
Please make the slideshow. Playing
Pardon?
the slideshow. Sir, the slide is constant. Please play the slideshow.
I'm not getting what you're saying. Slide is?
The slides are your, sir, your slides are not visible actually.
Not visible.
Please play slideshow. Now it is okay.
It is visible or not?
Everything is gone.
We saw only first slide sir till now. Now nothing is, but earlier that is light one, we saw that.
1 minute, 1 minute. I will just represent it. Okay. Now it is.
Yes, sir. Yes, it is visible now.
Okay. So, okay. So I will start with this slide. Now it is visible.
Yes, sir, it is visible.
Yes, sir. Yes.
So if you consider light, okay. So if you consider a light, then 3 parameters of light contain information. That is the amplitude, which is the intensity. Now, then we have a wavelength. Wavelength means the color of wavelength of the light means the color of the light. Now, the color of any object is visible because when light falls on any object, it only reflects one particular color, and therefore we see that the object has got some particular color. And then the third parameter, which we call as the phase of the wave. Now, during the reflection, light reflected from the different points on the surface, that is there is a change of phase. Now, these are the 3 parameters of the light which gives us information about the object. So this is about the phase of the wave. See, this is the uneven surface. Now the light is falling. Then from these troughs and crest, light is reflected. The phase of the light from the trough is different than the phase of the light on the crest. So these are the 3 parameters which are responsible for getting information of any particular object. Then we come to the lenses and the bending of light from the lenses. So we know light is refracted when passing from one medium to another, and the refractive index of any material is defined as a measure of how greatly substance slows the velocity of the light, and the direction and magnitude of bending is determined by the refractive index of 2 media. Now this is the phenomena of the phenomena in physics, that whenever the light travels from one medium to another medium, it bends. Now when say a light travels from say air to a glass medium, it will bend, it will change its path, and that change of path which we call as a refraction. Then the lenses which are formed to refract light. Now these are the optical objects which focuses light rays at a specific place called as a focal point. That is, and the distance between the center of lens and the focal point is called as a focal length. So this is the typical convex lens, where the rays of light will get refracted and will get focus, will get meet at one particular point, which we call as a focus of that particular length, and the distance between the plane of this lens and the this point where all the rays meets is called as a focal length. Now this is the property of a particular lens. Different lens may have different focal length, so the focus will depend upon the lens. If the lens curvature is more, the focal length will be short. If the lens curvature is less, the focal length will be larger. Now these are some of the things which we know. It's just the basic things that we use in physics. Now we come to the actual microscopes that are built with the help of these lenses. So there are various types of microscopes which I have put here. First one is a bright field microscope. Then we have a dark field microscope. Then phase contrast microscope, fluorescent microscope. So these are the one class of the microscope. Now the other class we will discuss later on. Now these are called are compound microscope, because the images are formed with the action of two or more lenses. So we'll then we have some other terms in optics which we define as a magnification. Now magnification, it is defined as the increase in image size with respect to object. So magnification is a measure of the enhancement of the image with respect to object. So let us see this figure. In this figure, a convex image is placed in front of convex lens. Then you will see that the image is enlarged. Okay. So this image is enlarged. Now this magnification depends upon the focal length. Focal length is focal length. If the focal length is low, then the magnification is high. If the focal length is high, the magnification is low. Then we have is defined as the ability images as shown. Now this you will see that nothing is there. There is something blur. Blur thing is here. It is not showing the exact nature of the object. Then the next one is the one where it is little bit better, but it is still blurred. Now if I go on, now this is the most clear picture. It is the letter R. Now in these images you will not see the great resolution. No resolution is there, or the resolution you may say is the poor criteria in the microscope. Some microscope may have better magnification, but poor resolution. In that case, that microscope is not so suitable to observe the objects, tiny objects. So resolution is also one of the property that a microscope must possess. Then these are the two images of a scene. Now this is a highly resolved image. This is a less resolved image. But in this case, the magnification is high. Here magnification is low, but in this case, the magnification is high. But it is a poorly resolved image because you cannot see the details of the image. Whereas in this case, you can see the detail of the images, but the magnification is low. So this is more magnified but less resolved. This is highly resolved but less magnified. Then mathematically, this resolution is given by this Abbe's equation. It is equal to d is equal to 0.5 lambda by n sine theta. Now, where n sine theta is what is called as a numerical aperture of the lens. If it is high, then the resolution is high. The resolution also depends upon the wavelength that you are using. That is the type of light you are using. If it is say the lambda is low, then resolution is high, because d should be less in order to have better resolution. Okay, so this n sine theta and lambda determines the resolution of the microscope. So for making highly resolved microscope, what we had to do is we had to make this quantity n sine theta higher and lambda lower, so that this microscope, the images are better resolved. So so if I use a blue light, then naturally the resolution will be more. And if I use a large numerical aperture, that means the size of the lens is large, in diameter, then also we can have a better resolution in the microscope. So the numerical aperture can be increased by using the oil immersion in between the objective and the object. That is, we put a oil of say cedar oil in between the gap of objective and this slide or the object, so that the numerical aperture increases, and that gives me the better resolution. What happened? Hello.
Hello, sir. You are audible and visible too.
Yeah.
Yes, sir. Slide is also visible, sir.
But it is not operating from here.
Oh.
Are you getting this now? Getting?
Yes, sir.
Yes, sir.
Sorry for this interruption. So the resolution of the object can be increased by increasing the numerical aperture and the wavelength, and using the lower wavelength. That means if the lambda is less, then the resolution is better. If the lambda is more, the resolution is poor. So as the numerical aperture, if it is high, then the resolution is better compared to the lens with a smaller diameter, numerical aperture. Then on the basis of this, let us come to the actual construction of a bright field microscope. Now this bright field microscope is again a combination of the several lenses, where you have a light source, then we have a condenser lens, then we have a slide or the specimen where we put, and this is objective and this is eyepiece. Now the light from the condenser lens is focused on this particular object, and then it is transmitted through this objective and the eyepiece to get the image. Now this light microscope produces optical images against the bright background. So the dark images are produced against the bright background. So naturally the contrast will be poor. That is the distinction between the bright and the dark patches will be poor, because the background is the bright background. So it is this typical microscope is used for biology, to examine the cells and other microbiological objects, and it is basic microscope used for lab studies. Now this microscope is a very basic microscope, and is used for the lab purposes. It is nothing, I mean, it cannot resolve the things the manner which we want, but still it is a basic microscope which is normally used in your laboratory. Now this is a typical microscope. Most of us know that this is the turret where various objectives are there. This is the eyepiece where we from which we see the images of the microspecimen, and this is the light source. Now this light source and this is the condenser arrangement which focuses the light on this specimen, where you can put here on the slide, and these are the objectives. The magnification can be changed by changing the various objectives by using this turret. So this is a typical microscope that you usually observe in various laboratories to examine the things. Now this is just various portion of the microscope, that is the arrangements to focus the objects and these things. We'll not go into much detail about this. So we come to the application of this bright field microscope. Now this bright field microscope is used to visualize the animal cells, plant cells, and morphology of bacterial cells and the protozoa. So the basic cells that are observed in biology are and the basic structure of the cell can be seen from this particular microscope. Then what are the advantages of this microscope? Now this microscope is very simple and very simple to operate, and it is also not so costly. So we can observe all the simple things with the help of this microscope. Now we come to the disadvantage of this bright field microscope. The resolution is poor. Okay, and this secondly, since we are observing the things under the background, bright background, then contrast is also poor. Now resolution is poor and contrast is also poor. Now this microscope does not have much magnification. You cannot increase the magnification much of this particular microscope. So these are some disadvantages of this bright field microscope. Now this led to what is called as a dark field microscope. Now this dark field microscope is the one where we observe bright objects under the dark background. In earlier case, it was a dark object under the white background or the bright background. This microscope is just like opposite of that. That means we are observing bright object under the dark background. Now with this, the contrast is improved so that we can see the better details in much better way. Okay, so this type of microscope is used. It is an improvement of over this bright field microscope, and this can be used for observing the details inside the cell. Now the arrangement is like this. in this case, it is similar microscope which we have earlier discussed to like the bright field microscope. It is a compound microscope. The only change that is done is this abstraction. This is the black plate is placed in between the light source and this condenser lens. So what happens is this light get blocked due to this black portion. The light from periphery of this obstruction will get through the object condenser lens and will get focused at the object, and now the objects will appear bright because the light is focused on this object itself. The background is now a dark. So what will happen is you are seeing the objects under the dark background, so the objects will appear bright rather than dark, which we have discussed in earlier microscope. Now the dark field microscope improves contrast significantly, and you can see the details of the object inside the object very clearly. So these are the two microscopes which we normally used in our laboratory to observe the microorganism. So now the advantage of these microscopes, they are very cheap, and they can be used. They can be operated very easily and can be used for observing the things. Observing the things which normally we used to observe in, like blood cells or some cells which are of general interest. Okay, so it is a effective technique. Dark field microscopy is an effective technique to observe the various microorganisms. Now still this has got a poor resolution. Magnification we cannot increase much, though we have increased the contrast to observe the details inside the cell, but still we cannot observe the details in much detail. This is the image that is formed by a dark field microscope. You can see the things inside the cell with the help of this microscope. See, the white dots are the objects inside a particular cell, and therefore you can see the things in much better way. But still we cannot see details of the objects inside the particular cell. So this has got disadvantage, that is, it has got a poor magnification, poor resolution, but the contrast is much better than compared to the bright field microscope. Now we come to the next microscope, which eliminates all the shortcomings in these simple microscope, that is the dark field microscope and the bright field microscope. Now this particular microscope is what is called as a phase contrast microscope. Now in this case, the phase contrast, the contrast is again improved as compared to the dark field microscope. So I have mentioned the demerits of the various microscope, that is the bright field microscope and the dark field microscope. So these are the disadvantage of the two microscope. Now the contrast is again improved if I use a phase contrast microscope. So phase contrast microscope uses the phase of the light to improve the contrast. Now how it is done, let us see. See, what is the phase? Phase of the wave is, see, waveform is just a time versus intensity graph, or the distance versus intensity graph. Now these are the two waves. One is with red color, one is with blue color or black color. Now these two waves are identical in every respect, except thing is there is a change of phase. One that is a red one starts early, whereas this black one starts later. So there is a phase difference between the two waves. Now this phase we can use to improve the contrast. So this is the basic principle of the phase contrast microscope. In this case, there is one plate which we call as a phase plate. Now this phase plate is of ocular in nature. We'll see how the construction of this plate. Now, whenever light strikes any object like bacteria, there is a lag in phase. So the light going through this bacteria will have a phase lag of say 1/4 of the wavelength. Now this light is passing through this plate where there is no phase change. Now in this case there will be no phase change. It will directly go. Okay. Sorry. Now this particular light has no obstruction, so it will directly pass through this phase plate. Now this phase plate introduces a phase change of say half wavelength. Okay, so what will happen is ultimately what will happen will be these two rays, when they meet at this particular point, then due to destructive interference, they will produce a black light or the black spot. So the objects will appear black as compared to the background. So there will be a phase contrast. A contrast will be developed because the light at a particular point will be dark, or the point will be dark, and other portion will be bright. So there is a what is called as a contrast will be developed, and this contrast we have generated because of the phase change of the light. And now this is a typical arrangement of the phase contrast microscope. So this is a particular what is called as a phase ring. Now this is an annular ring in which the phase, this annular ring, this portion, in this case the material is there which changes the phase of the light. Rest of the thing is a transparent material. Now whenever light passes through this transparent material, there will be no phase change, which usually happen with the light coming from the object. Whereas the light coming from direct light which is not going through the object will pass through this phase change ring, and therefore the phase change will be created, and this creates a phase difference between the light coming from the object and the light coming from the direct light, and this creates a say what is called as a destructive interference when they meet, and then you get a what is called as a contrast, because this light when interfere gets cancel each other and produces the bright spot. So this is so this is that working of this phase microscope. Now these are the images obtained from a phase contrast microscope. See this figure, you can see the details inside the particular this cell. So these are the images obtained from the phase contrast microscope. Earlier it was not possible to see the inside of the inside the particular cell, but now it is possible. You can see the details what is inside the cell. So this phase contrast microscope is a improvement over the normal microscope. Now the phase contrast microscope are relatively costly as compared to this bright field or the dark field microscope. Now I will not go into details of about the advantages and disadvantages. The only disadvantage is that this particular phase contrast microscope is is costlier as compared to the other microscope that we have discussed earlier. So, but however, this phase contrast microscope produces better images that as compared to the uh, bright field and the dark field microscope. Now we come to the another microscope, that is what is called as a fluorescence microscope. Now, fluorescence microscopy is one of the technique which is nowadays used in biology to examine the things. Now, this is a very powerful tool to examine the things. Now, now I'll just tell about this particular fluorescence phenomena. See, whenever any material, fluorescent material, is excited by a UV light, ultraviolet light, then there is an absorption of this UV light. Then the fluorescence is produced. That is, the light is produced from the material. So this light coming from the material is of lower wavelength, higher wavelength as compared to the excitation wavelength. That is, it is in the visible region. Suppose you excite a material with the help of, say, 300 nm light. The emitted light from this material may be in the green region or the red region or the blue region or the yellow region. Now this phenomena is called as a fluorescence. So some materials show fluorescence. That means when they are subjected to the UV light, they will appear as green or blue or some red color, so on. So this phenomena of fluorescence is used in fluorescence microscopy to create image or to see the image of the microcells. Okay, so these are the various objects. When you put a UV light, you will see that these objects will appear. Someone is red, someone is yellow, and so on. So all sorts of color is possible depending upon the fluorescence species inside the particular material. Now we construct a microscope using this phenomena. Now this is a typical construction of a microscope. Okay, so this is a UV light which is produced by a mercury vapor lamp. Now this is a filter which filters out the UV wavelength out of the various wavelength. Now this is a mirror which reflect that UV light, and this is our specimen. So specimen is placed here. Now as soon as UV light is you shine this with UV light, it produces color. It produces color. It may be in red region, it may be in blue region, it may be in green region and visible region. And this is a filter which filters out the whatever UV is left here inside this after this UV light strikes this particular sample. So the light coming here is only a visible region which we can see, and the objects when we see it in colors. So since the objects are self-emitting light, these objects appears bright. That's why fluorescence microscopy gives you brighter image, and the contrast is much better than the earlier microscope because contrast is in color. Okay. Yeah, so these are the few images of the fluorescence microscope. See, some portion is fluorescing red, some are blue, some are fluorescing. So you can see the detail of each and every micro things inside a particular cell. So this fluorescence microscope gives you better resolution, better contrast in order to examine the various details inside a particular cell. Now this fluorescence microscope is nowadays used in biology to observe the things because it has got it gives a better image as compared to the earlier microscope. And secondly, it is relatively cheap as compared to other microscope because you only have to use the ultraviolet light to and some filters to construct this fluorescence microscopy. Now some cells they are not naturally fluorescent. I mean, the cells, they are not naturally fluorescent. So what we do is we stain with some dyes, fluorescent dyes. Now this staining means putting the cells into some dyes, fluorescent dyes. A particular portion will absorb a particular dye, and when you see this specimen under the microscope, that portion will fluorescence, and you will get a fluorescence, and therefore that object can be clearly seen. So these are the advantages of the fluorescence microscope, that the fluorescence microscope is most popular method for studying the dynamic behavior of live cell imaging. That means you can see the live picture of the cells. So the sensitivity is very high. Sensitivity is very high, and secondly, the contrast is better, as we are seeing the light coming from the individual portion of this protein or cell, whatever, against the background of non-fluorescing material. So these are the some of the advantages of the fluorescence microscope. There are obviously disadvantages. That is, with UV light, the cell get degraded, or the dyes use changes its fluorescence structure, and after some time they will not fluorescence, and they will not give light. So these are some of the disadvantages of the fluorescence microscope also. Then we come to another type of microscope, which we call as a stereo microscope. Now the stereo microscope, is the microscope which gives you the ability to see the depth in the object. Okay, so normally what we have microscope, that is the bright field or the dark field microscope, they have only 2D picture, but the depth you cannot see in what is the depth inside the particular cell or particular object. So the depth is also one of the important criteria when we form an image. Now this stereo vision, we know what is the stereo vision, that is ability to see the depth of the object. Now these animals whose eyes are present side by side have ability to have a stereo vision. For example, human beings, we have eyes side by side, therefore we can have a depth perception of the object. Now other animals which do not have such thing cannot see in the object in 2 dimension. Okay, so what is the principle of a stereo vision? See, this is my object, this is my brain, these are my eyes. Now I am seeing the same object, this object I am seeing. Now my right eye sees this particular object differently, my left eye sees it with different angle. So I see the objects from the left eye, and I see the object from the right eye. You will see that there is a difference in weaving, and therefore when they are superimposed, you get a depth of the object. So this is the basic the principle of the stereo vision. Now on the basis of this, we can construct a microscope which we call as a stereo microscope. Now this is a typical stereo microscope where you have an objective, and these are the eye lens. Now object is placed here, and you put a light on this object, and this is my objective, and these are my eyepieces. Now this is the single objective. Objective is single, and the eyepiece, 2 eyepieces are there. One is adjusted for red eye, right eye and the left eye. Now when an image is formed from any object with this single objective and the 2 eyepieces, then you will see that the depth inside this particular object. So this is a typical stereo vision that I have discussed earlier. That means I'm seeing the same object with slightly different angle, which gives me the depth perception. Okay, so this is a particular a typical stereo microscope. These are this is the place where you can put a sample. This is lighting. That means I use the lighting to light the particular object. Mostly the stereo microscope, we use the reflected light rather than the transmitted light. So the light position is at this position, not under the object. Then we have this knob to focus the things. Then this is my stereo head where we have an objective lens, and these are the eyepieces. So I put a sample here or the object here. I switch on the light and focus the light, focus this particular stereo head to get the image of the object. So these are the images. This image is typically from a normal microscope, that is a bright field or dark field sort of microscope. Now this is the image formed by a stereo microscope. You can see the depth inside in those fibers. Whereas in this case we have a 2D image. So this is the stereo microscope image, which is very, very different from the dark field microscope. Okay, so stereo microscopes mostly used to see the scratches on the metal, or the where you want to see the depth of scratches inside a particular surface. You can use the stereo microscope to examine that. Then we come to the next microscope, which is the most modern microscope, you may say, which is called as a confocal microscopy. Now, in this microscopy, the light from only focus point on the image is allowed to detector to form an image. The other light is disallowed, thereby reducing background. So now I have in this particular picture, I am focusing only on this silence. See, I'm clearly seeing this silence. Rest of the things are blurred. So what I do in confocal microscopy, I only focus my lens or the instrument on the object which I want to see. Okay, so that is how I can see. I can see the things. If I do this, then what will happen is other background is reduced and I get only what I want. So this is the idea of the confocal microscopy. See, again I am showing this image. See, this portion is blurred, this portion I am under the focus. So I am seeing this portion only. Now this is blurred and this is under focus. So what I am doing is I am only focusing on those things which I want to see. Other things is in the background. Other I am not seeing. So then naturally with this you get a better contrast from the picture or the image. So this is the typical confocal microscopy arrangement, where you have a laser light, yellow laser light, which I am focusing here, and then I'm focusing this objective lens to only take light from this position, and then I have a detector which records the light coming from this portion only, and then I store this information, and then I form an image later on with the help of computer and so on. So this is my images formed with the confocal microscopy. This is a typical 2D microscopy, when that is the bright lens, bright field microscopy or dark field microscopy, you will get such type of image. But when you use the confocal microscopy, you get the detail of this particular image like this only. So the confocal microscope is much better than the other microscope. So here again there are images. The conventional light microscope will give you hazy thing. I mean, now this confocal scanning microscope, you will get a better resolution and better visuality of this particular image. Then we come to the next microscope, which we call as a scanning electron microscope. Now this microscope produces three-dimensional specimen surface features. Now in this case, we use the electrons reflected from the surface of the specimen to create the images. Okay, and now this, before going to this scanning electron microscopy, let us visit some of the things, resolution and resolution of the microscope. See, resolution depends upon two things. One is this numerical aperture, one is the lambda. If I reduce the lambda, if I reduce the lambda, naturally the resolution is poor. So if I use the electron which has a very low wavelength, then the resolution is much better. So this particular scanning electron microscope, or the images from scanning electron microscope, has much better resolution because the lambda of electron is much lower. Now this is the physics behind it. That is, the lambda is given by h by p. So if p is the momentum, so if p is very high, then lambda is very low. So if the electron has got very high energy, the lambda associated with has got very low value of the wavelength, and thus we get a better resolution. So this is a typical arrangement of the scanning electron microscope. This is the electron gun which is passed through the magnets. These magnets acts as a condenser lenses. In bright or dark field microscope, you have condenser lenses. In this case, in electron microscope, the function of condenser lenses are done by this particular set of magnets. Okay, and this electron is scanned over the surface of the material, and the backscattered electron are corrected to create an image of using a computer. Now this particular image which we form is much more detailed image. See, this is the image, a typical image from the scanning microscope. You can see that each and every detail in a very clear fashion. So the scanning electron microscope gives much more resolved and magnified image than as compared to the light microscopes. Okay, then we have another microscope which we call as a transmission electron microscope. Now the transmission of electron microscope is slightly different from the earlier one, that is a scanning electron microscope. In transmission electron microscope, transmitted electrons are collected and forms an image, whereas in scanning electron microscope, we scan the image and reflected electrons are collected to form an image. So this is the typical transmission electron microscope, in which you have a electron generator. Then again the condenser are there, condenser which condenses the beams of electrons into a beam. Now this this particular specimen is kept here, and now the electrons are going through this particular specimen, and they get diffracted, and then we form an image here. So it is just like a microscope, bright field or the dark field microscope, only the light is replaced by the electrons. That is the basic difference. So this specimen is similar to, similar to like putting a slide in the microscope, and then we get the image of this transmission electron image from the transmission electron microscope. Now this transmission electron microscope requires that the requirement is that the sample should be thin, and we need a sample preparation. Now this sample preparation is necessary because electrons do not get scattered much with the help of organic ions, that is the HCN. So we have to stain it with some heavy metal so that we create a background on which we get the images of the various cells made up of CHN. Now there are several methods by means of which you can make this staining of the material for transmission electron microscope. One of the thing is the shadowing, that is the coating specimen with a thin film of a heavy metal. Now this heavy coating specimen with a heavy metal produces a background, that is a under which we are observing the cells. Then there is a free etching method where you create a fracture inside the cell and put the carbon coating and see that carbon coating mold inside the transmission electron microscope. So this is how you make a freeze etching. That means you put this particular cell into say liquid nitrogen and then break it and then deposit the carbon on this particular cell to get a carbon replica of the cell and see this carbon replica under the microscope. So these are the various techniques by means of which you have to prepare sample for the transmission electron microscopy. Now these are the few images of the various viruses using the TEM. So this is the Ebola virus, and these are the various, this is the fly head of the very typical animal, fly insect. Okay. Then we come to this last technique or this last microscope, which we call as scanning probe microscopy. Now this scanning microscopy is used for observing the atomic surfaces. Okay, it is not used for biological purpose, but it is used for observing the atomic surfaces. And this is the first microscope which we call as a scanning tunneling microscope. Now this scanning tunneling microscope is based on the physics principle of tunneling of electrons under the field. Okay. Now this is a typical scanning electron microscope. Microscope consider, this is my sample. It is given some voltage. This is a tip. A tip is very important in the scanning electron microscope. It is usually made up of tungsten, and it is very sharp. Now this is my piezoelectric tube, which makes this particular tip move forward and backward with the help of a piezoelectric effect. And this tip is connected to the amplifier, tunneling current amplifier, and then the imagery circuitry. Now these are the typical components of a tunneling microscope. Now what happens is when I move this tip back and forth on the surface of this sample, and the tunneling current is produced in between sample and this tip. Now this tunneling current depends upon the surface morphology. That means if surface morphology as well as the bias that you give. So when I move this surface along the surface, then the tunneling current changes with respect to surface, and I get the signal which I record to form an image. Okay, so there are two modes of this particular microscope, which we call as a constant current mode. Now in this mode, the tip is scanned across the surface of the sample, and the height of the tip is controlled by this piezoelectric arm. So the height of the tip, now this is the formula. The profile Z or sample, now ZR is the sample surface. This is some constant value, and this D means the distance between the surface and the tip is recorded. So it gives me the corrugations of this atomic atomic structure on the surface of the material. Then we have another mode in which we can use this particular microscope is the constant height mode. In the constant height mode, the height is the same, but the current, I change the biasing voltage so that I get a typical amount of current. So that also gives me the image similar to the what we have we get in the constant current mode. So these are the two modes of this particular microscope, and mostly this microscope is used to examine the atomic surfaces and the surface topology. So these are few applications regarding the topography, spectroscopy, topological materials, and vortices on the superconductor. So all these microscopes have got typical operations. I mean, they are used for different purposes. Right from, say, simple microscope, they are used for simple purpose, whereas some advanced microscopes are used for detailed research in the field of microscopy and research. So I think I've given all the glimpses of all these microscope. See, each microscope is one topic for discussion or for presentation. I have covered almost all the microscope. I hope this will enhance your knowledge about the microscopes, and so that you can use them for your application, whatever field you are. So I stop here, and thank you very much for this presentation. Patience listening. Thank you very much. Hello.
Thank you, sir, for the wonderful presentation on microscopes and their operations. Very nice presentation, sir. Got a lot of information about the different types of microscopes that you have introduced.
Hello, Shubham. Am I audible?
Hope so that it will be very much useful to the researchers that they are present
Hello,
over there.
Shubham. Am I audible?
Over to Pooja, madam. Thank you, sir. Thank you so much.
Hello.
Thank you, ma'am.
Hello, Shubham. Am I audible?
Sir has given us glimpses of various microscopes. Most of us are researchers or upcoming researchers from various fields of science and technology, and we need to characterize and prepare materials for various purposes, and microscopy is one of them. Sir has explained very well the basic physics of microscope, starting from the basic bright field microscopy to STEM and TEM. Sir has explained it very nicely. Resolution was explained with the ability. Resolution was explained. Other than that, all the compound microscopes such as bright field microscope, dark field microscope, phase contrast microscope, fluorescence microscope, sphere microscope, and confocal microscopy was very well explained. Lastly, STEM, that is scanning electron microscope, and STEM, transmission electron microscopy, was explained very well. Last, scanning probe microscopy, which was used for observing atomic surfaces, was explained with constant current mode and constant height mode. Thank you so much, sir.
Thank you very much.
Thank you so much, sir, once again. Thank you.
Sorry for some technical problems. I never anticipated
that earlier. Yes, sir. But it was a very nice and smooth presentation. We really learned many things about the microscope.
So,
especially myself, I was not knowing about all those microscopes that you have mentioned today.
So all the
Thank you so much, sir.
Essential part of our research. Okay. So.
Yes, sir. Yes, sir. Yes, sir. Thank you so much, sir.
Thank you. Thank you very much.
Thank you, sir.